Hello everyone, welcome to the first video of my YouTube channel Breaking It Down. I'm Pritha and in this video we will learn what is meant by intersymbol interference. We will also see what causes ISI, what effects it has on a communication system and what can be done to avoid it. We will first begin by understanding what is meant by a multipath communication. When a signal is transmitted in the wireless environment, it undergoes reflection due to the presence of multiple objects in the surroundings like buildings, trees, cars, etc. When these reflected waves arrive at the receiving antenna, they all have traveled individual unique paths and as a result have different attenuations as well as different delays. Some of these reflected signals may even arrive with opposite phases and cancel each other out. Such a system where multipath signals exist between the transmitter and the receiver is known as a multipath communication system. As a result of combining of multiple attenuated and delayed copies of the transmitted signal at the receiver, the signal at the receiving end looks something like this. This apparent spreading of the transmitted signal in the time domain due to multipath reflections is characterized by a term called delay spread. Delay spread is defined as the difference between the time of arrival of the reflected wave with the longest and the shortest path, respectively. So, delay spread gives us an idea of how much our signal spreads in the time domain. Now, we know that time is equal to distance upon velocity, thus, delay spread can be easily calculated as d max minus d min upon c, where c is the speed of the electromagnetic wave. Another way to understand this multipath communication is to imagine the channel as a filter, which allows certain frequencies within the passband to pass and blocks all other frequencies. Also, let this channel bandwidth be denoted by B. Now, since the transmitted signals in a communication system are limited in time, they should ideally be unlimited in the frequency domain. However, the channel bandwidth, as we have seen before, is limited. This leads to filtering out of certain frequencies lying outside the channel bandwidth. Like in this figure, these frequencies will all be filtered out. This leads to filtering out of these frequencies, and the time domain system ends up spreading somewhat like this. This band limiting effect of the channel on the signal leads to the spreading of the signal in the time domain, as seen in this figure. Let us now gradually increase this difference between the signal bandwidth and the channel bandwidth and observe its effect on the time domain signal. So now we have reduced this channel filter bandwidth passband and this difference between the passband of the channel and the frequency response, and the signal has spreaded more in the time domain. Decreasing it further results to even more spreading. And finally, so as we can clearly see, greater this difference between the signal bandwidth and the channel bandwidth, higher the spreading of the time domain signal. Assuming the channel bandwidth to be constant at B, we can clearly see that a narrow band signal will have a lesser time domain spreading than a wider band signal. Now that we understand the multipath communication channel leads to delay spread in the transmitted signal, let us see how this delay spread leads to what we call the intersymbol interference. So, if subsequent transmitted signals are not spaced enough to counter the delay spread in the channel, the symbols at the receiver end interfere, as shown in this figure. This interference is what we call the intersymbol interference or the ISI, and it is undesirable as it can lead to decoding errors at the receiving end. Presence of ISI thus makes communication less reliable. One very intuitive way to reduce ISI now is to space these subsequent symbols sufficiently at the transmitter end. To achieve this, we can increase the symbol time t from 6 seconds to 8 seconds, which also leads to a corresponding decrease in signal bandwidth from 1 upon 6 Hz to 1 upon 8 Hz. However, while this, as seen in this diagram, will certainly prevent ISI, it leads to a very slow data rate and is absolutely incompatible to our modern high speed data requirements. So, finally, in this video, we learned that Multipath wireless communication results in multiple reflected copies of the transmitted signal to arrive at the receiver with different attenuations and delays. The difference between the time of arrival of reflected signal with the longest and the shortest paths respectively gives us the delay spread of the channel. This delay spread leads to time domain spreading of the signals. Imagining the channel as a filter with a passband bandwidth of B, a narrowband signal with bandwidth lesser than B will have less time domain spreading compared to a signal with higher bandwidth. Such time domain spreading of the subsequent received signals might result in ISI and as a result hamper the reliability of communication. ISI can be prevented by increasing the symbol time t, which is equivalent to reducing the signal bandwidth. However, this leads to slower data rates and is not practical. So, the question now arises that is there a way to reduce ISI without compromising on the data rate of the system? Well, turns out yes. And to know more about this, please check out the next video in this playlist where we introduce the motivation behind OFDM, the solution to all problems ISI. Thank you.